Hi everyone, this is my video number 25 and will be my last video for MTH 3101. Okay, and in this last video I'll talk on alternate series. Yeah, alternate series. So what is the alternate series? What is it? What is it? Alternate series. We define the alternate series as the series look like that n plus 1 un. Yeah? So if you list down that, so it give you when n equal to 1, so you have u1 minus u2 minus plus u3 and so on. Okay, it's plus minus plus minus, so that's we call it as alternate series. So for the convergence and divergence of this series, we have a theorem. I'm going to prove this theorem. Let this series minus 1 n plus 1 un be an alternate series with the property that with 1 we have un plus 1 less than or equal to un for n 1 2 3 4 5. Okay, which means decrease. Okay, and number 2 we have a limit of un that equal to 0. So therefore we have or then this series n plus 1 un converge. It is obvious from the previous theorem as well, if we have monotonically increasing or decreasing sequence and bounded, then the series converge. So in this case, for the alternate series, we have is decreasing, all right, and the limit goes to 0, then we say the series converge. Now to prove this, so we observe that as S2m, partial sum up to m. So this is u1 minus u2 plus u3 minus u4 and so on. u2m minus 1 minus u2m. Okay, you can group that. If you look at the definition here, that so what we have is un plus 1 minus un minus un plus 1. This is positive, right? Un minus. So by using that, so what we can see, this two u1 minus u2, this is positive, that one is positive, that one is positive. So it give all this term is positive. So therefore, so we have as 2m is positive. Yeah, from the properties given in the theorem. And we can also see that if you look at S2 we have, that is S2 u1 minus u2, we have a positive number, if we put S4 we are up to there, so we have positive that part, this one is positive, and we have plus there, so which means it means S4 greater than S2, and it's continuous, so it means S2 less than S4 less than S6 and so on. I hope you can see those. I repeat this. If you consider, let me write this. S2, we have S2 is U1 minus U2. It is positive because that one is positive. Alright, so this is positive. So S4, we have U1 minus U2 plus U3 minus U4. Okay, this is positive. This is positive. So all these things are positive. And obviously that because we have summation here. Alright, so from these two, we have S4 is greater than S2. And as well as if you put S6, S8 and so on. So what we find here, that S2 is less than S4, less than S6, less than up to S2M. Okay, and also S2M can also be written as U1 minus U2 minus U3 minus U4 minus U5 minus and so on minus U2M minus 2 minus U2M minus 1 minus U2M. All these in the bracket are positive. That one is positive. That one is positive. So, and we have here USM is U1 minus something positive, and so on. So which means S2M is less than U1. Okay. So therefore we have S2, you know the S2, this is positive, greater than 0 from the previous part here. Here we have S2M positive, and we have this as well. So S2 less than S4 less than and so on less than S2M, and this S2M is less than U1, so this is less than U1. Okay, so from that relation we have the sequence of partial sum 2M is monotonically increasing sequence, monotonically increasing sequence, and bounded. Why bounded? Because less than some numbers here. Increase and bounded. So therefore, since it's increasing and bounded, so it means the limit exists. So the limit as 2M n goes to infinity. Let's say this limit is S. Okay, but we can also write as 2M plus 1. You just need to add one more terms. From S to M, you add one more terms. So that gives you SM S2M plus U 2M plus 1. Okay. Now, if you take a limit of this, take a limit of S2M plus 1 is equal to limit S2m plus limit U2m plus 1. N goes to infinity, N goes to infinity, N goes to infinity. So from here we have the limit of Sm as shown previously, because Sm is monotonically increasing and bounded, so limit exists. So this limit we call it S here. Okay, and limit of Un is given in the theorem. That limit is 0. Yeah, limit is 0. So which means this limit is 0. So plus 0. Plus 0. So what we can see from here is that the limit of Sm plus 1 is equal to S. So which means, because Sm plus 1 is partial sum of our sequence, it means that this series m plus 1 Un goes to S, which means the series converge. Series converge. Okay, so the purpose now here is we want to show that Un converge. Let me repeat that. The purpose is we want to show that the series converge given each of the term Un plus 1 less than Un, and those things, limit of Un is 0. So what we do here in general is that first we want to show that the partial sum monotonically increasing, and we also want to show that boundedness, hence monotonically increasing sequence plus boundedness, that give you the limit exists. So we show that if for the partial sum for that series, you take a limit, give some value, means the limit exists. So it means that the sequence converge. Okay, so let's see some example. Let's say I have that series. Now we want to show either this is converge or diverge. We know that for positive terms 1 over m, for this series this is diverge. This is we know diverge. Okay, but now we want to test that series. Now if we use the relationship that Un plus 1 is less than Un, yeah, right? Plus less than Un. So I can write this Un plus 1 over Un is less than 1. So I'm going to show that Un plus 1 over Un less than 1. If I can show this, so it means that that series satisfies that condition, and we take a limit. Then we take a limit for each term, then it shows 0, then we can say the series converge. Okay, so if you do this, so Un plus 1 we have, so that we have U minus 1 N plus 2 over N plus 1 over Un, so you have N over minus 1 N plus 1. That give you, if you simplify that give you negative, and you have N over N plus 1. So definitely you have this is negative number, and you have this part here is less than 1. So because this is this N and N plus 1, so definitely less than 1. So this is less than 1. So therefore the first condition satisfied. Okay, the second condition, we take a limit, N goes to infinity, negative 1 N plus 1 over N, definitely this is goes to 0. Okay, so therefore those series converge. N plus 1 over N converge. Okay, you can also show that, let's say alternatively, you can write this series 1n plus 1 over n as 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and so on. You can show that this is less than this one. So how to show this? So from there you can write this is as 1 minus 1 over 2 minus 1 over 3, okay, minus 1 over 4 minus 1 over 5 and so on, minus and so on. So as you can see, this part of course this part is positive, this part is positive, and in fact each term after that is positive. So we have 1 minus something, 1 minus something, so definitely this give you less than 1, okay, because 1 minus something, so we got less than 1. So therefore the series minus 1 n plus 1 over n converge. Okay, can you try this? But I want to I leave it to you as an exercise. Say minus 1 n plus 1 ln n over n. Investigate the behavior of that series, of the series. All right. Now let's see definition. Okay. We have two things need to remember. Yeah. First, in this series, we say that series un. We say that absolute. We say that series absolute convergence if the series of absolute of un is convergence. Okay. And number 2, if that series converge but the absolute of that series diverge, then we say this series un is conditionally convergence. Yeah, conditionally convergence. Let's say example. If you look at this series n plus 1 over n, we know that we have shown in the last example this series converge. Okay, but we also know that if you take the absolute of this, that give you 1 over n. All right, and that series 1 over n, this diverge. We know this. So therefore, that series n plus 1 over n is conditionally convergence. convergence. And another example, this is first example, this is second example. If you consider that series 1 over minus 1 n plus 1 over n squared, okay, this series converge. Okay, this series converge. I want you to verify that series converge. You can follow the step that given in the first theorem of the alternate series. Then you can show that this series converge. Then, if you look at if you take the absolute of un, that gives you 1 over n squared, and we know that this series 1 over n squared, this is converge. Yeah, we already know the series converge. So that series converge. The absolute of that series also converge. So therefore we come up with that conclusion, n plus 1 over n squared. This is absolutely convergence, absolute convergence series. Absolute convergence. Okay, can you try this? If you have that series 1 over n sine n pi over 2, investigate the convergence or divergence of that series. Okay, now let me end this video as well as our lecture for the whole semester with this final theorem. Okay, we have theorem: if the series of the absolute of un converge, then series of un converge. Yeah, the other way is not happen that way. Not necessarily true. It means if un converge, it's not necessarily the absolute of that series converge. We have shown that, because if this converge, then we have two conditions. If that one converge, then it gives us absolute convergence. If that one diverge, it gives us conditionally convergence. But if the absolute of un converge, definitely un converge. Okay, so to prove this, given that in the theorem, given that series converge, okay, that series converge, and let Sm as u1 plus u2 plus up to and Tm, this is T1, u1 plus u2 plus so on up to um. Okay, Sm for the summation, that Tm for the absolute of that. Okay, so from there, if you add up those two partial sum Sm and Tm, Sm plus Tm, that will give us u1 plus u1 plus u2 plus u2 and so on, plus m plus m. Okay, so you can take this let's group then. Okay, So for this case, u1 and absolute of u1 is definitely less than 2 times u1. Okay, because u1 could be negative positive, you take absolute, that one is always definitely positive, then it should be greater than this greater than that. So this is also, you can do u2 and so on to um. Okay, and then of course I can rewrite this as a 2 u1 plus u2 plus um. And if you look at from there, they always give positive. Okay, if that one negative, that one positive, give you 0. If that one is positive, that one positive, definitely positive. So we have, and also we have Sm plus Tm is a positive, always positive. How do we know this? Just look at from there. If u1 negative, absolute of that positive, that give you 0. If that one positive, then definitely those are positive. So it cannot be less than 0. So all those things. So therefore we have Sm plus Tm. This is always positive from that. Okay, and this is from that less than 2 u1 plus u2 plus um. Okay, so what you can see from there, yeah, because from the theorem says that the absolute converge, so which means it's bounded and has a limit. Yeah, bounded and has a limit. So if you look at here, Sm bounded. Okay, Sm is bounded. If you just look at this, is greater than 0, is less than some number. So it means this is increased and bounded. Yeah, from this statement we have that series of sequence of the partial sum Tm increase and bounded. Okay, if increase, bounded, so therefore it's converge. So the converge limit exists. So we can write m goes to infinity, Sm plus Tm. Let's say this equal to some number L. Say. Okay. So from this, also I can write Sm is equal to Sm plus Tm minus Tm. This is true. Okay, so if we take a limit of this, we take a limit of Sm, this is equal to limit Sm plus Tm minus limit of Tm. For that, we have shown the equal to L. We say L. For this, because the limit exists, let's give some numbers. Let's say that limit goes to L naught, say. So which means the limit, this you have numbers minus numbers, so the limit exists. So therefore we have the limit of Sm exists. If the limit exists, so we have those series converge. Okay, so that's the end of the proof of this theorem. Okay, this is also the end of the not for the series. I'm not going to deal with a series of real function. You'll find this in the other subject, real analysis, I think. And this is also the end of our lecture for this semester. All right, so with that, I thank you, wish you a good luck in your exam and in whatever you do. Thank you. Bye bye.